Okay, work part two. So now let's talk about a lot of the typical problems where they talk about moving liquid in or out of tanks. Um, so I'm going to do a cylindrical tank to start off with. And let's say we have to move water out of this tank. And water is a standard in the metric system for density. Um, 1 liter of water has a mass of 1 kilogram, and a liter is 10 centimeters by 10 centimeters by 10 centimeters, or 1 decimeter cubed. The other way it's done is 1 milliliter of water is 1 gram. So the density of water then is 1,000 grams per liter, or just if you want to go that way, or there's 1,000 liters in a meter cubed, so the density of water is 1,000 kilograms per meter cubed. Now, if you were dealing with, say, let's do it in the English system. I think it's about 62 pounds per cubic foot. I kind of doing this off from memory. I think it's 62.5 or something like that. But so this is a weight density. This is a mass density. So you need to be, we're trying to do work by lifting water out of a tank. So to lift it, we have to do force times a distance. And the force is weight. So if you're in the, and a force is mass times acceleration. Now, if you're in the metric system and they give you the weight or the mass density, you have to take it times 9.8, or you have to take the mass density times the volume. So that gives you the mass, and then you got to take it times acceleration due to gravity. Do all of this to get a force. And then it's just times how far you lift it. Okay? If you're in the English system, you don't need mass density because they give you weight density. And so that's the acceleration is already in that. Mass density times acceleration is weight density. So if you're doing the weight density, of water, then all you have to do is multiply by the volume, and that will give you the weight or the force, and then times the distance you lift it. So you got to be careful about whether you're in the metric system or the English system. Okay, now in calculus, let's say this is a 3-meter tall tank, and it's filled with water for 2 meters, and you just want to pump it over the top. Well, it does the work. The pump takes each layer of this and takes it and lifts it to the top. Now, some students and some teachers get confused if they put the hose for the pump or a pipe clear to the bottom. They think, well, then I'm lifting it all the way from the bottom. But you're not, because if you put a pipe or a hose in the tank, the water will rise up to the hose to the top of the tank. And so you're just lifting the top water to the top of the tank. And then when that thin layer is off, then you're lifting the next layer that has to be lifted a little further, and then the next layer that has to be lifted a little further, then the next layer that has to be lifted a little further. So you can do a sum of how much work for each of these layers. So if you take just the top, let's just take the very top layer here and think about it. It's going to have a thickness. And if you're doing calculus, you want to make it a really thin thickness. Instead of a delta x, we call it a dx or dy, or whatever we want to call that thickness of it. So it depends on where you want to put your axis. And it doesn't really matter how you set this up. You could put your axes here, make this y and x, or x and y, it doesn't matter. You could put it in the center of the tank. You could put it at the top of the tank. You could put it at the top of the water. You just got to be consistent. So I'm going to set this one up. I'll just set it at the bottom of the tank. And then we can do it again, maybe putting it at the top of the tank. But let's set it there. And I'm going to call this x and this y. And so my thickness is in the y direction, so it's dy. And this is a disk, and the volume of a disk is pi, that wasn't a pi r squared h. Okay? Now, I didn't say how wide that tank is. It looks like it's got a radius of maybe 1.5 meters, just the way I drew it, scaling it here. So the volume of this slice is going to be pi 1.5 meters squared times the height dy. That's the volume of that disk. And I got to take the volume times the mass density of the liquid I'm doing here. And if it's water, it's going to be times 1,000 kilograms per meter cubed times the acceleration due to gravity. That is the weight of that disk. And how far do I have to lift it? Well, to get that disk to the top of the tank, I have to lift it 1 meter. But the next disk here, I have to lift it a little bit further. And the next one a little further and a little further, and then it's going to keep changing. So I need to come up with an expression for how far I'm lifting each of these. Now, if you try to say, well, I want to lift the top one, and then the next one, next one, the next one, next one, it gets a little confusing how to do this here. But if you just say, well, I'm going to lift the bottom one, the next one, I'll work our way up, then the first one will be lifted 3, and the next disk would be 3 minus how much higher it is, and the next one is a little 3 minus that. So it's going to be 3 minus x. And then I want to calculate this, add these all up as y, 3 minus y, excuse me, that was in the y direction, 3 minus y, and add them all up from y going from 0 to 2. Now, let's do this same setup. I'm assuming you can do this because these are all constants come out, and you just got to integrate 3 minus y dy from 0 to 2. Let's say we set the coordinate system at the top of the tank. So I'm going to redraw my tank. Still 2 meters deep. And I'm lifting it to the top of the tank, which is 3 meters high. So now it's going to be 9.8 times 1,000 kilograms per, and this is meters per second squared, times kilograms per meter cubed, times the volume, which is pi 1.5 meters squared, times the height, which is dy. I'll just keep it, I'm putting the same coordinate system, but at the top of the tank. So y is still here. I'll put y at the bottom, positive y down here, x is here. And this is all the weight of the disk, that's the volume of the disk, times the mass density, which gives you the mass, times 9.8 gives you the weight, the force that you have to lift it some distance. And the distance you're going to lift it, now y is here, so you're going to start with y, and you're going to lift it from 1 to 3. Putting it here, the first y will be, the first one will be lifted 1, and then it'll be 1 point a little bit more, one all the way down to when you're lifting it from the bottom up 3. This one makes it's a little easier to understand, but if you do the math on this and the math on this, you'll get the same answer. Now, what if we were doing this in the English system? Okay, so the tank I drew is 3 meters high, so let's just call that roughly 10 feet high. It's the water's filled up, not all the way to the top. Let's just call it 6 feet. So the answer will be a little bit different because these are just approximations. The radius, instead of being 1.5 meters, let's make it 4 feet. Okay, so now to get the work on this one, we have to do a slice. And I'll put the coordinate system at the top of the tank again. I could put it at the top of the water, but I'll just put it at the top of the tank. I'll make this be the positive y down here, the x here. And so the weight is going, the force, the weight will be, let's see, the force, I'm going to write it down here since I've got it off the page. Force times distance, the force is going to be the weight. And I have a weight density of 62.5, I believe, pounds per foot cube, cubic foot. So I have to take that times the volume of a slice, which is going to be pi r squared times the height of that disk, which is going to be, again, dy, which is in feet. So that's feet cubed, cancels feet cubed, and I get pounds, a weight that I have to lift it this distance. And that distance, since I'm starting here and y goes down, it's going to be y. And I'm going to add those up, lift that top layer, the next layer, the next layer, and the next layer. Work my way down, and so it's going to be from 6 feet. The first one's got to be lifted 4 feet to the last one that's got to be lifted 10 feet. Okay, so here I don't have to worry about multiplying by gravity. I have a weight density as opposed to a mass density, which I have to multiply by acceleration due to gravity. Times the volume to get the volume of that. So I get the weight density times the volume gives you the weight, which is the force you're working against times the distance you have to lift it. Okay? And you can see the difference between putting the coordinate system at the top versus the bottom. We could have put it here, and then it would have been, let's see, let's do that. What if I'd put the coordinate system at the top of the water? And I'll do the English one here. So it would have been 62.5 pounds per foot cube times the volume, pi r squared times the height, dy. I'm still leaving y here. I'll just put y positive there, x there. So the thickness of this slice is dy. And how high do I have to lift it? And you can get all tangled up in deciding whether that's a positive or negative and whatever. Don't worry about it. You're lifting it 1 foot. 1 plus the next slice is going to be a little bit more plus the y value. Integrated from now, y is going to start at 0 and go to 3. And if you work this out and work this one out, you should get the same answer. Oh, not 0 to 3, 0 to 6 feet of water. Okay? And we have to lift it not 1, but, boy, I'm looking at my mistakes here, 4. You're lifting it 4 feet. I'm thinking of the one before in meters. So we got to lift it to 4 feet, and then 4 feet plus a little bit more, a little bit more, a little bit more, until the y gets all the way to the bottom. So from 0 to 6. So the last will be lifted 4 plus 6. 4 plus 6. Okay. So that's just the basics of work. Now, you could want to talk a little bit here about the cylinder. It's a uniform all the way down. So it's pretty piece of cake. In fact, you can figure out how much work it takes to lift this to the top by just going to the center of this, figure out the total volume of this, times the mass density, times gravity, get the weight density, and lift the center of it, because the top would have to be lifted less, the bottom would have to be lifted more. You can just take the center and lift it to the top, and you can get it. You don't have to do any calculus whatsoever. It's when the container changes shape that makes it more of a calculus problem. So we're going to go on to that. So now let's make it a conical tank. Let's do one that's this way. Okay, let's make it again 1.5 meters. Let's make it, looks like I drew this a little bit taller. Let's make this 4 meters. And let's say it's filled to 3 meters. Okay, so here's the top of it, and let's just say it's still water in there, so it still has that 1,000 kilograms per meter cubed mass density, or 9,800 newtons per meter cubed as a weight density. Okay, let's say we're just lifting it to the top of the tank. Where do you want to put your coordinate system? Well, we saw on the last one that it's kind of easier to put it at the top of the water, but we could put it at the top of the tank, or we could put it at the bottom of the tank. It's completely up to you. I'm going to choose to put it at the top of the tank. And again, I'm going to make my positive y down here and my positive x there. That's kind of backwards for what students like to think. They like the positive up there, and then you get into the negatives issue, and I don't. Just Just make it easy on yourself. Okay, so we're going to take a slice of this, and this could be any old slice in here, and its thickness is in the y direction, so it's dy. Its volume is pi r squared dy. And we take that times the weight density, which is 9.8 meters per second squared, times mass density, 1,000 kilograms per meter cubed. And this has units of meter cubed, so the meter cubes cancel, and we get mass times acceleration, which is a force or a weight. There's the weight times the distance we got to lift that slice. So if that slice has to be lifted, y. It just has to be lifted from here to the top, and y is 0 here, so this is y down to here. So, and I want to integrate this. My first y will be, the first layer that I take off will be at 1, and the last one will be at 4. By just adjusting these and putting at the top, I've got my work to lift the water out of this. Except that I have y, and I have another variable r. So I need to remove r from this whole thing. Now, this is the r. That's in the x direction. So we need to solve for x, r equals x, but we need to find out what that is in terms of y. Now, if I put my coordinate system here, you can do triangles, similar triangles. X is to this as x, or r is to this as this is to this. 1.5 is to 4. Or you could, and that's the common way to do it. So I'm going to show you another way. We can just, since we've got our coordinate system on here, this point is 1.50, and this point is 0.4. So we can just write the equation of a line going through those 2 points. Y minus y1 equals m. See the slope here. Change in y is 0 to 4. 4 over minus 1.5 times x minus 1.5. And if you solve for x in this, add 1.5 to both sides. And then multiply by minus 1.5 over 4. That's what you can use for your r in this equation. If you did similar triangles, you'd get a similar value. So you can use your Algebra 1 skills using the coordinate system to get it. You could also just say r, or x, is to this, which is 4 minus y, as 1.5 is to 4. And I believe if you work these two out for solve for y, you'll get the same thing. Okay? All right. If this was in the English system where they gave you this in feet and whatever, then you would be doing just the 62.5 or whatever the weight density of water is times the volume, and doing all the same kind of stuff. Um, I could move the coordinate system to the bottom. I don't know if you need me to do that. I will, but I'll move on. Let's do another one. Let's do more complicated one. A tank laying on its side, like an underground tank that might have gasoline or diesel or some kind of oil in it or whatever. Let's do this one in, let's do it in the metric system still. So let's say it's got oil in it. So oil's density, you can look it up, but it varies. It's around 600 kilograms per meter cubed. It's lighter than water, less dense than water. Now, when we do these, and let's say we have to lift it not just to the surface, but to the top of the tank. But let's say we have to lift it up, say 6 meters. The ground might be buried under 1 meter, and we want to lift it up 5 meters higher for some reason. I don't know, to get to the top of a truck or something. Okay. Now, when I have a sideways circle like this, I prefer to have my students just say, put the coordinate system right at the center of the circle, the circular end, because then the equation of the circle becomes simpler. If that's 6 meters, this might be 3 meter radius. The formula for this here, if we put the coordinate system there, x, and we'll put positive y up there for now, then the equation for this circle is x squared plus y squared equals 9, the radius squared. Okay, now let's say this tank was, if it was completely full, I would do this in 2 steps. I would do the top half, and then I would do the bottom half. Let's just say it's half full, and so I'll do the bottom half. So I'm going to take a representative slice, which is now going to have a thickness, and since up and down is y, and the length, I didn't make it here, so let's make it be 5 meters. And so it's a rectangle. Okay. Actually, I'm going to put the positive y down here. Okay. So how far, let's see. Let's go through the steps here. First of all, this is mass density, 600 kilograms per meter cubed. I have to take it times 9.8 to make it a weight density, meters per second squared. So that's a weight density, which I have to take times volume. To get, this is a mass density, mass per volume, times the volume to get mass times acceleration, which is a force that we have to take times the distance that we're going to lift it. So I have to need the volume of this. Well, that's just a rectangle. It's, well, let's see. It's this direction. If I got a point on this circle, any point on this circle, if that's my coordinate system, it's over x and up y. So it's, this direction is x. And so this length is 2x and times 5. So I got width times length times thickness. And there's the volume times the mass density times acceleration due to gravity gives me the weight that or the force that I have to work with. And then I have to lift it a distance. Well, the distance is going to be 6 meters plus 3 meters plus y meters. So that's 9 plus y. That's the distance I'm lifting it. And I'm going to add these up as y goes from 0, the top slice, if this is a half full tank, down to the bottom, if I'm going to completely empty it, or if I'm only going to go down to a certain distance, whatever that is. If I go clear to the bottom, y is going to go from 0 to 3. If I were doing the top half of the tank, I'd make my positive y up here, and I would have a slice, and it would be y would go from 0 to 3 if I'm emptying the top half. And the distance I'm lifting it is 9 minus y. It'd be 9 minus y here to empty the top half of the tank, going from 0 to 3. So that's lifting the oil out of the tank. Again, if they'd given me the weight density in the English system, pounds per cubic foot, then that would replace this. These are constants, so they come out. That would also come out, but the rest of this would be same, other than we would be talking about how many feet in these different places, but same idea. Okay, was there another one I needed to talk about? Nope, I think that's it.